You and I have spent a lot of time discussing all the different kinds of matter around us and the fact that it's made of these tiny, tiny building blocks called atoms. Now, these atoms really are very, very, very small. So small that we certainly can't see one, we can't see 1,000 altogether. In fact, if you were to line up atoms side by side, if you lined up 1 billion of them next to one another, they would take up about this much space, maybe a little more, a little less, depending on the atom that you chose. They are truly tiny. That also means that any simple object that you might have, even something like a pencil, contains billions and billions and billions of atoms. So you and I need a much more convenient way of communicating very, very large and very, very small numbers. Now, there are a couple of ways that we can do this, a couple of different ways that we can change the magnitude of our measure. First of all, what different types of measures might we be discussing? A very common measure for us is mass. Mass is a very convenient measure of quantity, and it's something I'm sure you use in your day-to-day life. Another very common, convenient unit of measure, which again, I know you've seen before, would be volume. We can measure the volume of a substance in litres or in millilitres. Another very convenient measure. Volume specifically tells us the amount of space that an object occupies. Finally, a third measure we could discuss length or width or height, so using distance to define how large or small something is. When we're doing that, we might use meters or centimeters or kilometers, millimeters, again, but some derivation of the meter. So what do we do with these units of measure when we want to communicate the very large or the very small? We actually have two different options, and you and I have inadvertently been using one already, and I'll bet you haven't thought twice about it. That first option is to use prefixes to put things like milli or kilo or centi in front of the measurement, and that changes the magnitude. A good example for us, you can picture a can of soft drink. A can of soft drinks are often sold at this size, that's 375 millilitres. But what does that mean? That little M out the front of the litre, milli. That means 1,000th of. So when they're saying you've got 375 millilitres, what they mean is you have 375 out of 1,000 litres, or 0.375 litres. So these prefixes, really good way of changing our scale, changing our magnitude. And again, I'll bet you do it all the time. You might buy drinks by the milliliter, you might buy potatoes by the kilogram, where a kilogram is just 1,000 grams. Again, they enter your lives everywhere. But what about when that's not really sufficient? What about when we want to talk about really big and really small numbers? That leads me to our second option, and that's scientific notation. I have an illustration on your screen for you to help us represent scientific notation. If you have a look, scientific notation is represented with a single digit here at the front, followed by our decimal place. We then have any subsequent digits there to help us describe the number that we're talking about. But then down here at the end, this is the important part. This times 10 to the power of, that's what gives our number magnitude. If we've got a very large number, this might be times 10 to the power of 3 or 10 to the power of 6, and that will move the decimal place 3 or 6 places to make it a bigger number. If we've got a really, really small number, we might say times 10 to the power of -2 or 10 to the power of -5, something that will move the decimal place to make it a very small number. This is scientific notation. So once again, just a single digit, 1 through 9, allowed before that decimal place. Any other digits that you want after the decimal place, and the times 10 to the power of is what gives it magnitude. So here we have the planet Neptune. The planet Neptune is a funny creature. Its orbit around the Sun actually changes a little bit as it orbits around. But typically, it's this far away from the Earth. It is 44,000,000,000,000,000 meters from the Earth. That's a long way. That's a very inconvenient way of putting it. We could also just use our words and say that this is thousands, millions, billions, trillions. We could say it's 4.4 trillion meters away from the Earth, but scientific notation is going to be a convenient way to look at this. So how do we decide what this number would be in scientific notation? Well, we know that for scientific notation, the decimal place has to go here, after that first 4. So how many places do I need to move the decimal place to get there? It has to move 3, 6, 9, 12 places. So if I wanted to represent this number in scientific notation, it would be 4.4 times 10 to the power of 12, because I'd need to move the decimal place 12 places to get to the original magnitude of the number. Make sense? Let's try a few more examples together, either going from scientific notation to standard, everyday, or going from everyday back to scientific notation. Right, so our first example here, I've got a very small number, 0.000000023. It's painful to say, it's painful to write. Scientific notation is going to be much, much more convenient. So our decimal place, it needs to move 1, 2, 3, 4, 5, 6, 7, 8 places. So I could rewrite this as 2.3 times 10 to the power of negative 8. Need to move that decimal place 8 places back in order to get to the original number. Let's try going the other way, from scientific notation back into standard everyday notation. So 5.23 times 10 to the 4, that means I've got to move the decimal place 4 places to make this a bigger number. If you're having trouble visualizing it, try scribbling in a few extra zeros so that you can see where the decimal place belongs. So 523, let's put a few zeros there, and then we move it 1, 2, 3, 4 places. So if I write that as a normal number, that's 52,300. And the one down the bottom, again, scientific notation back into normal, 8.4 by 10 to the minus 3. I need to move that decimal place 3 places to make it a smaller number. Jotting in some extra zeros, again, might make it clearer to see. So I'm going to put a few leading zeros in. Our decimal place is originally here, so it has to move 1, 2, 3 places back. So that would be 0.0084. So now you and I have scientific notation, a means of expressing really large and really small numbers to one another. And that's going to come in handy when we get to our next topic, where we'll start describing the atom in a lot more detail.